Three of my colleagues will give you an today. I, Yash Madhogaria, along with three of my colleagues, will give you an example of an application of artificial intelligence in the field of mining. Before going forward, let me give you an idea about the different methods of mining. So the two different methods of mining are open cast mining and underground mining. So in open cast mining, the minerals are extracted from an open pit in the ground, and in the underground mining, the minerals are extracted from below the surface of the earth. And the method to choose the different type of mining is based on the relative closeness of the mineral deposit. Now, let me give you an idea about the mining operation in an open cast mine. So, in a typical mining operation, firstly, the overburden or the waste rock is charged with explosive and then blasted, following which a shovel and a dumper is assigned to that location where the shovel job is to load the muck into the dumper and the dumper's job is to transport the muck to the assigned location and return back. So it is clear that the trucks routing along open pit mine is an important link connecting all process flows and external transportation tasks for mineral and waste, which is one of the key factors that directly influence the cost of transporting systems. According to the statistics, it is generally believed that the transportation costs account for more than 50% of the total operation cost. In open pit mines that use trucks as the major means of transportation. Based on this, let us consider a problem. So, in a large open pit mine with trucks as a main transport equipment, there are usually several routing nodes in the road transport system. In the given scenario, there exists a single dumper and a single shovel in a mine, including multiple dumping points. Our goal is to find an optimal route for the dumper to make its way to the dumping location and back forth. So the network typically looks like this, where A represents the starting node of the dumper and I and H represents the goal node or the dumping point. Now my friend will tell you on how to approach this problem further.
Hello everyone, my name is Sayan and today I'm going to discuss about depth first branch and bound algorithm which is useful for the shovel dumper problem in our mining industry. So there are depth first branch and bound are a class of algorithms which help us in finding the shortest path or in some cases longest path from the goal node to the from the starting node to the goal node. So basically the depth first branch and bound is like a depth first search, but here we use the idea of pruning. So how do we do that? So basically what it happens is we in this depth first branch and bound, the idea is to maintain the lowest cost path to a goal found so far and identify that as the bound. So if during some search we encounter some path where cost plus that edge weight of that path, here HP denotes the edge width, is greater than the bound, so we can easily say that this part can be pruned. So that subgraph starting from node P will be pruned. So if a non-pruned path is found to a goal, then we must return it because that will be the best cost. Now let's go and look at the pseudocode of this algorithm. So in input we have a graph with n nodes. Arcs are the edges of the graph. S is the start node, and goal is the node from where we want to end. We generally use a heuristic function on the nodes and initially the initial bound we send it to infinity. The output which we show is the least cost path from the start node to the goal node. Or if there is no path exists, then we output an empty list, which indicates that there is no path from the start node to the goal node which is optimal. So what we do is we run a searching algorithm and recursively we search. So if suppose if this is the sequence of path, it starts from n0 to n1 to nk, and if it is less than bound, then we go and explore the subnodes there. But if that is greater than bound, then we prune it. Finally, we come out of the loop and then we output our answer. If it contains the sequence of nodes from start to the goal node, then that means there is a satisfactory path with optimal cost. Now let's run this out on the toy example. So as you can see in this slide that A is the starting point. So in a typical mining scenario, A represents the point where the shovel works in an taking out the overburden and puts it into a dumper. Now the node colored H and I are the goal nodes in this problem. And this is the point, these are the dumping zones. These are the dumping zones. Other nodes like B, E, F, C, G, and D, these are the nodes which are the intersection points, or these are called as the bench road intersections in mining terms. Now we can see that there is a cost associated with it. So we have to choose the best cost for this graph. And as you can clearly see, the answer would be A, D, and H with a cost of 5 plus 19, which is 24. Now let's see how the depth first branch and bound algorithm works. So first what we do is, so first let's initialize the cost to infinity. We start the algorithm from the start node. So A, then we go to B, then we go to E, and finally we go to I. So that cost will be 10 plus 8 plus 14, which will be 10 plus 8 plus 14, and that the cost becomes 32. So since the initial cost was infinity and the new cost is 32, we can just update the cost of this. So this becomes 32. Now we go back to B and backtrack from here. So and then we recurse again. So now from B we will go to F. The cost here will be 17. Then from F we can go to E, but 17 plus 18, that would come to 35. Since 35 is greater than 32, we can be sure that we are sure that this path will produce more cost, and hence it can easily be pruned. So we don't go and search for E and I once again. So we backtrack again. From F, I can go to G, so that would be 18, and then from G I can go back to H. So 18 plus 13. So once we reach the goal node, we see that the cost has come to 31. Since this cost is less than the previous best, we update the cost to 31. Now we start again from the start node and we backtrack back to A, and we start from C and we go on exploring. So C, then G, then H, like this way: A, C, G, and H. So that the cost would be 12 plus 5, 17, and 13, 30. Now since this is less than the cost which we have found, we update the cost with 30. Now we start again from, we backtrack from C and we update it. 7 plus 1 8 and 13. So 7 plus 1 8 plus 13 is 21. 21 added to 12 is 33. So 33 wouldn't be updated because we have found a cost which is lesser than 33, and hence 30 will remain there. Now we start again from D and we follow this path. A, D, and H. So here the cost will be 5 plus 19, which is 24. Now, as you can clearly see that 24 is less than the previous cost of 30, so the best cost gets updated. Now we have exhausted all our search paths and we have found out that the best cost is 24. Hence, we return this value. So we can clearly see that the dumper should follow this trajectory to have an optimal cost. Now my friend Manideep will show you another search algorithm which is used in the mining scenario, and he will try to compare the running times as well as the space complexity of all the other algorithms. Thank you.
Hello, my name is Manideep. Now I am going to explain the A star search algorithm. This algorithm can be used in scheduling of shovel dumper systems, which is very similar to the commonly known traveling salesman problem. The shovel is a loading machine which is usually deployed at a fixed place, which is basically static. A shovel loads the dumpers with overburden, and the dumpers are basically huge trucks that carry overburden from shovel to dumping points or locations. Our goal is to find an optimal route for the dumper to make its way to the dumping location and come back efficiently. Let's see if A star search algorithm could be of any help to us. Now let us look at a simple representation of the problem. As shown, node A, which is colored in blue, is the loading point where the shovel loads the dumpers, and the dumping points I, H are colored in brick red. As shown, specific nodes are connected by specific edges and each edge has a specific cost. Best first search is popularly known as A-star algorithm. It is an extension of breadth first search. The search is basically guided by a function fn. Fn is sum of edge cost and heuristic for that particular node. Here is the flowchart of the A-star algorithm. The most important part of this algorithm is it has two lists, open list and closed list. What it does is calculate the fn values at each node and put the minimum of those fn in the closed list and open the daughter nodes if there are any of the closed ones. Here's a look at the problem again. Now let's see how we'll solve this. So firstly, we'll start with A, and as A has no cost, we'll just close it and open its daughters B, C and D. And out of B, C and D, D has the lowest cost. The Fn value for D is lowest. So we close D and we keep the B and C just as they are, and then we open the daughter of D, which is H, and write it down as shown. And then what we do is we'll look for the minimum value in the open list in B, C and H. So the B has the minimum value, so we close the B and then we open the daughters of the B and add them in the open list and then see what's the minimum, and we keep on repeating the process, and then keep on repeating the process until we get the minimum cost, and when we reach the end node, we terminate the algorithm. So this way we can find the shortest path to the node, to the end node, and also the minimum cost. If we continue solving the problem, the first end node to get closed will be H with a cost of 24. Hence A to D to H will be the most recommended path as it is the least costing one. Thank you for listening.
Hello, I'm Shourya. By now you may know three algorithms to find out the most optimal path in for the dumper. Now we'll compare them all in the mining scenario. In most of the surface mine, none of the parts are permanent. All the parts are temporarily built for the extraction of the ore. So the paths are very irregular, are rough and bumpy. So, so we need to find out the most optimal path considering the time of operation and and the condition of the roads also. For example, if we take the tire on a rough surface, the tire of the dumper can wear out very quickly, which is very high, which is very expensive and will lead to very high maintenance cost. Similarly, a bumpy road can lead to the failure of transmission system and the suspension system, which also leads to very high maintenance cost. So in mining, it's very crucial to find out the optimal path, which also saves times and also reduces the maintenance cost. So in the given example previously, there are very few nodes, but in actual case, there will be multiple nodes with very high cost and very variable cost depending upon the path and the bumpiness, roughness, and multiple other scenarios. And also, these paths will be changing over time very frequently. So we need to find out the algorithm which is fast in of multiple nodes. So for that, we have written a sample code to find out which is the most optimal case for in mining with multiple nodes. So let's go ahead and see that. Here's the a simple code which we wrote, which generates a random graph with 100 nodes and run DFS, BFS, and A star on it and find out which one works best for it. So let's run it and see what are the output. So when we run, we find out that A star takes a minimum time that is 0.009 seconds, and DFS and BFS are slower than that. It is because A star doesn't re-explore nodes. Although the RAM consumption is very high in A star, but in case of mining where the nodes are very large, A star performs better. Therefore, it is the most optimal for mining case. Uh, so with this we can say that these kind of optimization method using artificial intelligence in mining can be very beneficial, both for cutting cost and for saving time. If we implement these kind of methods in mining, the production rate could be higher at much less cost, as we are reducing the cost of maintenance very highly if we choose the right path. And this can help mine, mining industry a lot. Thank you.